Let's get some practice doing k-means clustering and hierarchical clustering. So I've opened up the RMD file for practice set 5 on clustering, and what I'm going to do is to define some of these custom-made functions to make data processing a bit easier. So from here on out, very often what you'll find are some useful functions at the very beginning of the practice page documents, and so I recommend reading those in. I also recommend having loaded up the clustering summary.r for this particular practice set. And in the future, each data mining unit is going to have a set of summary code that walks you through how to fit some of the models or implement some of the algorithms that we've been discussing. So a very useful summary that not only contains the functions that we just read in, but gives a little bit more description of what those functions do and illustrates where we use those functions. All right, so question number 1 asks us to perform a customer segmentation, and we're going to use the k-means clustering algorithm to do so. So what we're going to do is we're going to read in this data file. So I'm going to make sure my working directory is in the right place. Let's read in the data file, and we're asked to null out the channel and region columns because these are customers to some sort of distributor, and this is the amount of money that each of the customers is buying on each of 6 different categories. The channel and region are demographic information, and we're not interested in doing clustering based on those values, so we'll just get rid of them. All right, so we first need to do a little bit of data cleaning to make sure that we can do clustering. We're asked, are there any missing values that need to be replaced? All right, well, there are a few ways to check to see if there are any missing values. If we get a summary of the data frame, we could look to see if there are any rows that are NA. If there are NAs, we'll have additional row here in each summary. That gives us the number of NAs. Looks like we don't have any. Another thing that we can do is look at the output of the function complete cases. So complete cases will go through each row of a data frame, and it will return true if every single column of that row is present, and it'll return false if at least one of those columns is missing. So if I run complete cases, I get a bunch of trues saying, hey, I have data in every single column for each row, and because true is the number 1, false is the number 0 in R, if I ask the mean of this logical vector, I get a 1 back. So everything is complete, we're all good. We have complete information, we don't have to worry about handling missing values. Now the last part of this question asks why can't we do clustering on the data values as is? Well, let's look back at a summary. One thing that we know is that in order for each variable to contribute equally to the clustering scheme, they need to be on the same scale, meaning that they need to vary over approximately the same range of values. Now the smallest values for each of these columns is right at about 3. Here's one that's 25. But the largest values are definitely quite different, going anywhere from around 40,000 up to over 100,000. And if we look at the quantiles, the medians, we see that there is quite a bit of variation going on. So they're not varying over the same range of values. So some columns are going to be preferentially treated when the clustering scheme takes place if we don't do anything else. And that's bad. We want each column to contribute equally to the clustering scheme. And the other thing that really prevents us from doing clustering as is just the shape of the distributions overall. So if we go through and actually just look at the histograms of each one of these variables that we have recorded, we find highly skewed distributions. And we know that that's kind of a bad thing to do clustering when we have skewed distributions because that opens us up to outliers in the tails of the distribution to have undue influence over what those clusters look like. So when we do clustering, we want each variable to have equal say over what the clusters look like, and we want each individual, more or less, to have equal say as well. Dealing with skewed distributions gives extra weight to those individuals in the tails of the distribution, and we'd like to avoid that. So we already have the response written here. There's no missing values, but because of this extreme skewness and because the values in the column are varying over different ranges of values, we'd like to do some data processing before doing clustering. All right, so we're asked to copy the whole data frame into a data frame called data processed. That way, when we manipulate some of these columns, change some of the values, we're not modifying the original data. We'd like to avoid that if possible. So we're going to do all our data processing on data.processed. And what are we going to do? Well, we're going to go through each column and try to figure out some sort of transformation to make the distribution of values as symmetric as possible. All right, so here's where I'm going to jump on over to the summary file, because for all these summary files, I'm going to walk you through the process on how to do the data processing, fitting the models, etc. And this is no exception. So in this case, I'm illustrating how we do clustering with the ex6.wine dataset in reg class. And we need to do the transformation to symmetry if necessary. We need to do some scaling so that each variable is varying over approximately the same range of values. And we have to handle categorical variables if they exist. So something very similar to what we're asked to do, copy the original dataset into something called data.processed, and then to start looking at the distributions. So what I'm going to do actually is just copy these 4 lines of code and just borrow them over here and change the column names and data frame names when appropriate. So let's go ahead and look at the very first column of the whole data frame. Very skewed, so all right, is there something better that we can work with? Well, suggest transformation is one of those functions that you read in at the very top of the document. What it does is it goes through various transformations of the original values to look for something that's a little bit more symmetric. So specifically, how does this work? Well, we'll give it the values in the first column of the whole data frame. And the transformations that we're going to try are taking the original values and raising them to some power. Very often, when we find the right power, the resulting distribution is going to look roughly symmetric. So the only exception is when we try to raise something to the 0 power, we can't, because raising something to the 0 power just gives us 1 back. So when we try to raise something to a 0 power, that's understood as instead taking the logarithm of the original values instead. So what we're going to do is we're going to try raising the original values from the powers 0, 0.5, 1, 1.5, 2, etc., understanding that 0 really means log 10. So we'll run this, and it says, all right, I suggest taking the log base 10 to the original values. Okay, well, does this make sense? Let's go and actually look at a distribution of the logarithms of the values in the first column. And indeed, we find it looks quite a bit more symmetric. A little bit of skewness now here on the left, but it looks a lot better. I would say that we'd accept this transformation. It looks better than where we started. So let's go ahead and left arrow into the first column of data processed, the log of the first column of whole. All right. So we've done this now. We've handled the first column, and guess what? We just have to do this methodically for each one of the columns here. So, got a copy and pasting. In this case, we only have 6 columns, so just a bunch of changing 1s to 2s, etc. Let's try it out. Very skewed. Let's try to find a transformation. It suggests log base 10. You'll see that a lot in business analytics. This is beautiful. It looks extremely symmetric, so we definitely accept that transformation. We'll put into the second column of data processed the log of the values in the second column of whole. And we just do this again. I'm going to copy paste this a whole bunch of times. And this is just where we have to make sure that we're changing the numbers in the right places. Let's check out what's going on with the third column here. The histogram of the values in the third column, extreme skewness. Can we do any better? Let's try a transformation. Log base 10 is what's suggested. So let's look at a histogram. Very symmetric, one tiny outlier out here. That's all right. So let's go ahead and replace the values in the third column of data processed with the log of the values in the third column of whole. All right, well, let's try the fourth column, very skewed. What transformation does it suggest? Log base 10 again, very common in business analytics. Beautiful, so symmetric. We accept that transformation, and we'll go and put those values into the fourth column of data processed. Fifth column of whole, very skewed. Can we do better? Log base 10 again. What does that look like? Pretty symmetric. Kind of bimodal maybe, but much better than where we started, so we'll accept that transformation and put in the fifth column of data processed the transform values. And finally, last but not least, we have the sixth column, very skewed here. Can we do any better? Suggest log base 10 once again. Pretty nice and symmetric, so we're pretty happy with that. We'll accept that transformation, and we'll go and put those transform values in the sixth column of data processed. All right, so we've gone through each of the 6 columns. We've done some transformations. And we've replaced the column of data processed with those transform values. So the only thing left what we have to do is scale the data so that each column has a mean of 0 and a standard deviation of 1. And this is so that each column is varying over approximately the same range of values. This ensures that each column contributes roughly equally to the clustering scheme. All right, well, how do we do this scaling? Let's go on over to that summary document and let's see where that scaling takes place. So when we scale, what we're going to do is we're going to use that function scale data frame. That's one of the functions that you actually read in at the very top of the practice document right here. Scale data frame is just going to go through each column of a data frame. And if it's numerical, it's going to go ahead and replace the values with the scaled versions, mean of 0 and standard deviation of 1. So we take data processed, we run it through scale data frame, and we need to left arrow that back into data.processed so that we replace the values in data processed with the scaled versions. So did it work? Well, let's look at a summary of data processed. The means are 0 here all throughout, so that's good. What about the standard deviations? Well, summary doesn't give us that information, but if we use the apply function, apply will go through each column or each row of a data frame and calculate something with each of those values. If we put a comma 2, that's going to go through each column. What do we want to get for each column? Well, the standard deviation. SD is the name of the function that gets us there. And so we see that the columns all have a mean of 0, standard deviation of 1. They vary over approximately the same range of values. They're all roughly symmetric. We can do some clustering now. All right, so the question becomes, how many clusters do we want? So k-means requires us to basically input in the number of clusters to do that clustering scheme, and so we should come up with a reasonable value for the number of clusters. And so the first thing that we do is to make the elbow plot to see if there's any sort of natural structure that exists. Sometimes there are just widely isolated clusters of individuals that share common sets of characteristics, and if that's the case, we'd like to discover that. And the elbow plot will help us discover that if that is indeed the case. So how do we make the elbow plot? Well, let's go ahead and look to see what the summary document tells us. Notice we skipped over step 3 because we didn't have any categorical variables. We didn't have to worry about that. But here's our code for creating the elbow plot. I'm just going to copy and paste here. And what is it doing for us? Well, we're defining a vector called possible.k, which is the integer sequence 1 up through 15. And that's actually what it wants us to do here. We want to investigate values of k, the number of clusters, from 1 to 15. We don't know it's going to work ahead of time, so let's try out everything. And what we do for each value of k is we run the k-means algorithm. So we have our for loop that defines a looping variable called k. It's going to go through one by one each value in the vector of possible k. And what it's going to do is it's going to run k-means on our process data, symmetric, mean of 0, standard deviation of 1, with k number of clusters, and with 2 additional arguments here. So what do these arguments actually do for us? Well, iter.max is telling us the number of times the k-means algorithm is allowed to iteratively figure out where the cluster centers are and who belongs to what cluster. If you remember how k-means works, you randomly pick k different locations in the data space to serve as your initial cluster centers, assign cluster membership by whichever center you're closest to, that's who you belong to, and then you re-update where those cluster centers are just by looking at the center of mass of the initial cluster identities here. And then you iterate. So we kind of bounce back and forth between reassigning cluster memberships, figuring out where the new cluster centers are, etc., etc. So 75 is telling us we'll go through that process up to 75 times. Very often we'll reach convergence where we don't get any change in cluster identities only after a couple iterations here. But we'll allow it to go up to 75 in this illustration. And in this case, 25 is what I suggest you guys to do, so we'll change that to 25. And then end start is actually the more important parameter here. So one thing we know about k-means is that if we restart the algorithm with a different set of initially picked cluster centers, we might actually end up with a different set of cluster identities. That's because k-means is trying to solve, mathematically, a really hard problem, and we're just using a heuristic to come up with a solution. So n start is important to have as a fairly large number so that the k-means algorithm is restarted numerous times so that we find the best clustering scheme with a certain number of clusters. And n start of 50 is very generous here. N start of 50 basically almost guarantees us that we're going to get more or less the best clustering scheme for an input number of clusters. All right, and then the $ tote.within.ss is basically telling us, well, how tightly clustered are those individuals around those cluster centers. We want smaller values. It's kind of measuring how loosely packed the individuals are. So smaller values of loose packedness is better. We want things tightly clustered. So, all right, a lot of explanation for a very little code here, but let's run it and let's interpret it. So each dot is representing that WCSS, basically a measure of how loose those clusters are around the cluster centers. Smaller values means that we're getting more and more tightly packed around the cluster centers, which is a good thing. And we look at this elbow plot and treat it like a bent arm. And we're looking for the elbow of that bent arm. And in this case, we don't really see an elbow. We see just kind of a slow decrease that kind of slows down as we move on to higher and higher numbers of clusters. And this is pretty typical. This tells us there's no natural structure that exists in the data. If we did see any sort of natural structure, the way that would be represented by the elbow plot is it would go down up to a point and then really just flatten out for the rest of it. And where that elbow is, that's kind of the natural number of clusters as suggested by the structure in the data. And we don't really see that here. Okay, so no natural structure. The WCSS just continues to decrease ever more slowly as the number of clusters increases. So no natural structure. We need to basically just decide for ourselves how many clusters we want to deal with. And so this is very often the case. We say, all right, well, let's start out with 3 clusters. Let's see what the interpretation is. Maybe try adding an additional one to see if we get any additional insight to the problem. All right, so we're going to generate 3 clusters and talk about them. So once again, let's head on over to the clustering summary document. This tells us how to fit a scheme for a particular value of k, 4 in this particular case. So let's borrow this code. In this case, we want to generate 3 clusters, so I'm going to say center equal to 3. We're going to use itermax as 25 and n start of 50. And the important thing here is that we're going to use set seed of 474 immediately before running the k-means algorithm. This is important just for reproducibility because at the end of the day, k-means is going to assign to these clusters numerical labels, cluster 1, cluster 2, cluster 3. And if you don't do set seed, you might actually get a different cluster number for a cluster, which makes interpreting the clusters and comparing results a little bit difficult. But if we do set seed, we'll all recover the same set of cluster centers, the same cluster labels, so we'll go with that. So we want to make a table of the number of clients in each cluster. So, all right, that sounds good. Let's go ahead and do table k-means $size. So 3 clusters here, and we have 81, 147, and 212 members. In fact, I don't even need table. Just k-means $size tells me that I have 1 cluster with 212 members, 1 cluster with 147 members, and 1 cluster with 81 members here. All right, well, let's look to see what these clusters look like. This is the code that I just copy-pasted. If I look at the $centers component, that's going to tell me where the center of each cluster is. I don't need too many digits, so I'm going to round to just 1 digit here. So here are my cluster centers for cluster 1. That one had 212 individuals. Cluster 2, 147 individuals. Cluster 3, 81 individuals. And we're going to go and look to see if there are any cluster-defining characteristics and come up with a 1-sentence description of the clients in each cluster. So here are the skills that you'll really be bringing to the table when you're doing analytics for a company. So what do these numbers mean and how do we talk about them? You know, any person can run the k-means algorithm here in R. It takes a special type of person, a trained person, to actually give meaning to these results. So how do we talk about these clusters? Well, one thing we look for are values of 1 or higher, either positive or negative, as we scan through the cluster centers. Remember, what these values are telling us is basically relative to the individuals as a whole, are the individuals in this cluster above average or below average? So positive numbers mean above average, negative numbers mean below average, and the farther away from 0, the more different the individuals in those clusters are from the overall average. And so that's why we look at values like -1, +1, -2, +2. The farther away from 0, the more different those individuals are from the typical individual. So if we scan through the numbers here, we don't really see all that much interesting except for this -1.2 and this -1.1. That means that the individuals in cluster 3 are very below average in regards to these two measurements. So the amount that they're spending on fresh and the amount they're spending on frozen are well below what the typical customer in the dataset spends. So these are two cluster defining characteristics. Cluster 3 have very below average values of fresh and frozen. And just kind of scanning through, slightly above average values for milk and grocery and detergents, paper, and a bit below average for delicatessen here. So with only two numbers that are kind of noteworthy here, going towards +1, -1, +2, -2, we have our work cut out for us. We need to look at other aspects of the clustering scheme to characterize what these clusters look like. And that's when we start scanning through and looking at the values across one row. And I'm going to look at cluster 2 here because it's actually a little bit easier. If I scan left to right, I see that I get positive numbers for every single one of these 6 measurements. So that's telling me that across the board, the customers in cluster 2 are above average in terms of spending for each one of these 6 characteristics. So these are kind of like the superstar customers. These are the high value customers that are spending above average in every single category. And so that's pretty noteworthy here. So customers in cluster 3, well below average in fresh and frozen. Customer 2, basically above average in everything. Well, what about the individuals in cluster 1? Well, if we look, it's a mix of positive and negative. It's not all that far above 1 or above 0 or below 0. But if we compare what's going on with cluster 1 and cluster 3, we see that they're kind of polar opposites. So in cluster 1, we see positive for fresh, cluster 3, negative for fresh, negative for milk, positive for milk, negative for grocery, positive for grocery. So it looks like individuals in cluster 1 and cluster 3 are kind of opposites. There's nothing that really sets individuals in cluster 1 apart from the typical individual on a column by column basis. But as a whole, it looks like what we have are the high value customers in cluster 2. Cluster 3 has those customers spending well below average values for fresh and frozen. And in some sense, the individuals in cluster 1 are opposite of what's going on in cluster 3. Above average where individuals in cluster 3 are below average, etc. So we'd have to write that down in words, but that's essentially what we're looking for when we go and do these cluster defining characteristics. Do we see values far from 0, positive or negative? If so, that definitely catches our eye. We don't see stuff like that. Well, we kind of cruise through each row and look left to right to see, is everything positive, is everything negative? And then we start comparing clusters to one another to see, all right, are the individuals in each of these clusters kind of opposites of each other? All right, another way to look at this visually, sometimes it's a little bit daunting to look at a bunch of digits here, is to run the par-chord plot from the mass library. So if I load in the mass library, go over to the summary here and say, okay, well, where's par-chord? How would I run this? Well, one thing we can do is run par-chord on the k-means output as follows. So in this case, we only have 3 clusters, so I'm going to go the color of 1 through 3. And we can look visually to see what these clusters look like. Now, there's not really many labels here. It's not a fantastic plot, but it does add some insight and really captures what we were discussing just in words. So red must be cluster 2 here, above average in everything, the high value customers. Cluster 3, that's actually the green, well below average in fresh, well below average in frozen, above average in milk, grocery, etc. And we see that cluster 1, the black line, kind of acts oppositely of the cluster 3, the green line. When green is high, black is low, and vice versa, except for this delicatessen here. So hard plot to read. Basically, there's no y-axis here. So going up the y-axis just means more above average. Going down on the y-axis means below average. The zero is not even marked here for exactly where the average is because it's just really a relative scale that's going on here. But it gives you a good impression of what's above average, what's below average. Red above average across the board, black and green lines kind of working the opposite of each other. So some pretty useful insight, kind of interesting to look at. Takes a little bit of getting used to, but some tidbits of information lurking in there. And if you want to see what the responses were that I actually wrote up, go ahead and check out the solutions. I'm not going to write them out here because it's quite a bit of writing here. All right, part E asks us to do some more clustering, because really the best way to choose the number of clusters is to basically repeat what we just did, but adding one additional cluster to the scheme. So we saw that the elbow plot didn't really suggest a natural number for the number of clusters. The basically loose packedness of the clustering scheme gets smaller and smaller and smaller as we add in more and more clusters, so things are getting more tightly packed as we add in more clusters. So the question just becomes, do we gain any additional insight when we move from 3 clusters to 4 clusters? So, all right, it says, well, let's do this for 4 clusters now and see if we get any additional insight. So we can literally just borrow our code from up here and change one number. So instead of having 3 centers, we basically want 4 centers here. If we do this, we can look to see, all right, now it looks like we have this number for cluster 1, 2, 3, and 4. And if I look at the centers of these clusters, these numbers match up. Now, one of the drawbacks about k-means is that cluster 1 doesn't really correspond necessarily to cluster 1 when we had 3 clusters. Cluster 3 in the 3 clustering scheme doesn't necessarily match up to cluster 3 when we do 4 clusters here. What are calls cluster 1, 2, and 3 are kind of just assigned randomly. So it's not like we know that cluster 4 is the new cluster that emerged. It doesn't work that way. So we actually have to look back and see, is there some sort of correspondence between where we started and where we ended up going from 3 to 4 clusters. And sometimes really the whole impression of what our clusters look like completely changed. So in the 3 cluster scheme, we had this cluster 2, which was all above average in everything. And as we scan through, we don't really see that anymore. The closest we get is cluster 1, which is above average in everything except for frozen, just slightly below average. And in fact, all of a sudden, we have a big old 1 here, which catches our eye for detergents and paper. So actually what each cluster looks like is quite a bit different as we go from 3 to 4 clusters. The question just becomes, all right, is this 4 clustering scheme useful to us? So is this additional cluster worth it? Well, let's just go and see what we see. So number 1, we look for those cluster defining characteristics. We're looking for anything that exceeds 1 or -1, and we do see quite a bit of that. So cluster 1 had this detergents paper well above average. Cluster 2, very below average for fresh and frozen, and somewhat delicatessen. Very similar to what we saw with cluster 3 in the 3 clustering scheme. Individuals in cluster 3, well, no 1s or -1s or 2s or -2s here. So if we look relatively closely at these numbers, we see they're kind of opposites of cluster 2. So we got negative, positive, positive, negative, positive, negative, kind of similar to what we saw with that interplay between cluster 1 and cluster 3 here. All right, well, what about cluster 4? Well, we do see some cluster defining characteristics, really. -1s in milk and grocery, and really detergents paper as well. It's pretty close. And at the average for fresh and frozen. So cluster 4, really quite coincidentally in this case, really looks like a new discovery for us here. Basically, customers that have very far below average values for milk and grocery, but average values for fresh and frozen, below average for detergents paper, and below average for delicatessen. We don't really see an obvious analogy to one of those 3 clusters that we saw before, so that's a new bit of insight, a new cluster of individuals that are spending well below average for milk and grocery. So is that interesting to us? Well, we really got to talk to the boss at this point. We've got to ask ourselves, what are we trying to get out of this clustering scheme? Is this new discovery useful to us? But this is what we do with clustering. This is why it's so hard, is that it requires a lot of input from us. We need to know what's important ahead of time so that we can attribute meaning to the clusters that are emerging from the k-means algorithm. So once again, if you want to see what I wrote up, go ahead and download the solutions file, and I have a pretty detailed response of what that additional cluster is, if it's worth it, etc. I'm not going to type that out here. So question 2 asks us to basically redo our analysis, do some customer segmentation, but with a different approach for clustering, hierarchical clustering. And I actually like hierarchical clustering for business analytics a bit better because it is a bit more intuitive to move from 3 to 4 clusters, 4 to 5 clusters, and to immediately grasp what that additional cluster is really getting you. So it's a little bit easier, I think, to ascribe meaning to the clusters and talk about what's the appropriate number of clusters for the problem you want to solve with the hierarchical clustering scheme here. All right, so what we're going to do is we're going to run hclust, our routine for hierarchical clustering, with the defaults. So one thing we have to decide when doing hierarchical clustering is how do we measure how far apart two clusters are? Do we measure that as a distance between the two closest individuals between the two clusters, the two farthest individuals, the average distance? A lot of different ways, and that's a choice we have to make here. So let's go and look for hclust here to see how we do it. All right, so I'm going to borrow this line of code, and it says it wants us to run it with the default, so I'm not going to even say method, because by default it's going to do it with this complete linkage. Complete linkage, I'd have to look up what that is. I still get confused between complete and single. It's measuring the distance as either the two closest individuals in the two clusters or the two farthest distances. You'd have to look that up here. We're going to move into a different clustering method here with Ward's D2 metric. So that's the one I prefer, but we're going to try this out. All right, so we've done this on data processed. And then what we're going to do is we're going to plot the dendrogram. So one of the more intimidating things to interpret in business analytics, I gotta say, but once you get used to it, it's not so bad. So when we plot the dendrogram, yikes, that looks like a lot of stuff, but remember, it's not that intimidating. Basically what we do is we read the dendrogram from the bottom going up. This height is really a misnomer. It's really talking about the distance that clusters were when they get merged together. That's really what those numbers are corresponding to. And the numbers themselves really aren't all that interesting. What we're going to focus in on, though, is basically the process of merging as we go from the bottom up to the top. Now, there's so much stuff going on here that I'm actually going to go and do export, save as PDF, and I'm going to change this to something ridiculous, like 30 by 30 inches. I'm going to go to preview so that it makes just a really, really big plot. And this allows me to talk a little bit more about it. So I'm going to zoom in. That's the nice thing about looking at a PDF version of the plot. I'm going to zoom in super, super, super far. And I'm going to talk about this. So you'll notice that each line is actually labeled by a number. What this number corresponds to is the row in the data frame that contains that individual. So here is the line corresponding to individual 11, the 11th row. Here we have individual 377 in the 377th row. And what we see are these vertical lines going up, 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 and then they get joined together right here. So what does this mean? Well, this is an important thing to understand with a dendrogram. Essentially, what we're doing as we're moving from the bottom to the top is we're looking to see which individuals get merged together to become clusters, and then what clusters get merged together as well. Whenever we see a joining of these vertical lines, that means that some sort of merging took place. Remember, with hierarchical clustering, we start out with every individual in their own cluster. Then we merge together the two individuals that are the closest together to make our very first cluster. And we keep on merging. Whoever's closest to each other, either individuals or clusters, they get merged together to make bigger and bigger clusters. And eventually, when we get to the very top of the dendrogram, way up at the top here, kind of skipping from where I was at, Here we have one cluster, another cluster here. Everything that dangles from the vertical line all belongs to the same cluster. These two clusters get merged into one to make just one overall big mega cluster here. All right, that's going way back down to where we used to be. This is basically what we talk about with the dendrogram. Where did individual 11 go? I don't know. So we'll talk about these two instead. So 327 and 391, these two vertical lines, they get merged together right here. And if we scroll to the left, that corresponds to a height of about 1 or so. So that means that those two individuals were about 1 unit distance apart. All right, so if we look at the dendrogram as a whole, what we see as we move from the bottom to the top are individuals getting merged together, clusters getting merged together, and we're actually going to mostly ignore what's going down here in the bottom because what we can use the dendrogram for is choosing the number of clusters in our scheme. So what we say is that we cut the dendrogram at some height. So if we were to cut at a height of 9, that means making a horizontal line going across at 9. And wherever that horizontal line crosses one of these vertical lines, everything dangling from that vertical line is going to be a cluster. So if I cut at 9, all right, everything dangling from this line is going to be a cluster. If I follow down to the very end of those lines, I actually see that that cluster only contains 2 individuals, individual 76 and 153. If I continue on towards the right, I hit this vertical line. Everything dangling from this line, which contains a lot of stuff we see, all these individuals belong to one cluster. If I continue along, here's where 9 intersects this line. Everything dangling from this vertical line. So if I go down here, everything from about here over to here makes another cluster. And then everything dangling from this line, once again at a height of 9, is going to belong to another cluster as well. So everything from right about here onwards, we could actually look to see the individual numbers, the rows that correspond to the cluster in this case, if we look really hard. But we can kind of see, all right, who's in what cluster very easily from the dendrogram. And what's nice is that if we want to just split one of the clusters that we have into 2, it provides us a really easy way to do that. Because we could say, all right, I have my 4 clusters, cutting at 9, boom, 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 boom. If I said, all right, I want to split this cluster up once more, well, basically I look to see what's dangling off to the left and to the right when we split that cluster. And I immediately know that in those 2 clusters that are merged, whatever's dangling from this left vertical line here are going to be the individuals in one cluster, so not so many of them. And in the other cluster, everything else that dangles from this vertical line. So the dendrogram, really, really interesting when you get into it, but how are we going to use it here? All right, so in this case, what we're going to do is notice that some individuals join the clusters very late in that merging process. So what we want to find are some of the outliers. So these outliers are going to be labeled by their row numbers as they join this dendrogram really, really, really late in the game. So remember, each individual gets their own label here. And what we see is that like individual 339, that's this vertical line right here, actually joins up with this far right cluster when we're reaching a distance of about 8. So individual 339 is like way, 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 way off there in the data space. So the closest individual that they're next to in the data space is like 8 units away. That's really far because we see that most of the merging takes place at distances between like 0 and 2 here. Most of the individuals are pretty close to each other, and so they're getting merged together really, really quickly into clusters. And as we expand out the distance at which we're merging stuff together, things are getting big really quickly. Individual 339 is so far out there in space, we have to go out to a distance of 8 units before we find their nearest neighbor, basically, and they actually get merged together in one of those clusters. So individual 339, really different from the rest of the individuals, and we see 2 other individuals joining really late in the game. I wish I wouldn't have closed that. If I go to Save PDF, let's make it 40 by 40. Let's make it insanely big. If I go to my preview, zoom in on what's going on over here, it looks like individual 76 and 155 joined very late in the game as well. So let's look to see what makes these guys so unusual. So I'm going to cancel out of here, and we're going to look at 75. Well, I really should have paid attention. I don't remember. 339. That's the guy over here on the right. And then once again, let's see if I can zoom just using the zoom and get any sort of insight. No, I can't. So I'm going to do this one more time. 40 by 40 preview. And let's find these crazy two individuals that don't join till very late in the game. 76 and 155. All right, so 76, 155. I'm going to print out these individuals. I'm also going to look at a summary of the entire data frame. So why are these guys so far apart? What makes these guys so unusual? Well, number one, row 339, the smallest value for fresh. So definitely very set apart here. Very small value for milk. Grocery, kind of right in the middle here, not unusual with respect to grocery. Frozen, definitely on the higher end of the scale. Detergents and paper, very near the bottom. And delicatessen, kind of near the middle here. So this individual is just so unique in terms of their fresh, basically, that really sets them apart. All right, individual 76, well, what do we see here? Well, the smallest value for detergents, paper, the smallest value for grocery. So very unusual in those regards. Individual 155, very small value for detergents, paper, very small value for delicatessen, etc. We can actually get a different view of what this, how these differ by looking at the rows of the process data frame, where we now get basically above versus below average. And so look at this, wow. So this first row here corresponding to individual 339, so far below the average value of fresh, very far below milk, pretty much smack dab in the middle of grocery, actually well above the average for frozen, well below detergents, right above the average for delicatessen. So very unusual customer, very unusual combination of characteristics here. 76, what made this person so unusual? Well below average value for grocery and below average for detergents. Individual 155, very small across the board and extremely small values for milk, grocery, and delicatessen here. So some pretty interesting stuff you can get from the Dendrogram. You can actually spot outliers. What makes these individuals so unusual from the rest of the rows in the data fairly easily. All right, so now here's where we're going to use the ward.d2 metric to figure out how far apart the clusters are. So what's this ward d2? Well, basically it looks to see how far away are individuals from their cluster centers. So if we're going to merge two clusters together, what we're going to do is we're going to start out by looking to see, well, what is the typical distance from individuals from their two cluster centers? And then what's the new typical distance when we merge those clusters together? So they'll be a bit farther apart because we only have one cluster center. Things are going to be a bit more spread apart around that new cluster center here. And that ward.d2 measure is how much basically that typical distance between individuals and that common cluster center has increased when we go from two cluster centers down to one. So when we go from two down to one, individuals obviously are going to be a bit more farther apart from that cluster center. So ward D2 is measuring that numerically. So we're going to go and rerun this dendrogram or this hierarchical clustering scheme with ward D2. And this always gives us a much prettier looking dendrogram. And this is why I like it. So if we plot this dendrogram, all right, a lot less action going on, a lot more merging taking place at distances very, very close to zero here. Most individuals are pretty close to each other in the data set. We still get individual 155 sticking out like a sore thumb. But this allows us to basically choose the number of clusters and talk about those clusters a little bit more easily. So I like this one because it's not as sensitive to outliers as the default method or some of these other distance methods, and it gives a prettier looking dendrogram. All right, so if I were to cut at a height of 11, basically a distance of 11, how many clusters would emerge? Well, how many clusters would emerge? I just look to see how many vertical lines do I cross. 1, 2, 3, 4, 5, 6, 7, 8. I would get 8 clusters from a scheme where I had a cut at 11. And I could immediately talk about, all right, who's in what cluster. Everything that dangles from this little vertical line here belongs to a cluster. Everything that dangles from this vertical line here, also a cluster as well. And I can see, if I could read these numbers, who actually belong to which cluster immediately. All right, so kind of cool. Let's go ahead and make 4 clusters, though, and just compare what those clusters look like with k-means. So how do we do this? Well, the cut tree command, if we take the name of our hierarchical clustering scheme and say, I want 4 clusters, this actually outputs the cluster identities for each individual in the data set. So what we're going to do is we're going to add these cluster identities to the log scaled version of the data. So data.processed. We're going to add a column. What do I call it in the summary notes here? I just call it $HC, so we'll use that. So we'll add a column called IDHC to be the results of running cut tree on the scheme for 4 clusters. All right, so we're going to do this, and then we're going to use aggregate to find the mean value of each variable for each cluster. So we're going to say aggregate dot, basically every single variable, twiddle IDHC. We want to look at every single variable broken down by the possible values of IDHC in this data process data frame. And what function are we looking at? Well, we're looking at the mean here. And we're going to round this to 2 digits. Or 1 digit, because that's what we did before. Oops, no extra thing there. All right. So let's go back to the k-means. And I'm going to copy and paste this down here so we can compare. All right, so this was k-means. Comment that all out. And here's our hierarchical cluster scheme. So different way of approaching the problem, so potentially completely different clusters that might emerge. So as we scan through these numbers, once again, we're looking for the numbers that are far from 0, either positive or negative. And here's one. Cluster 4, it looks like we have negatives across the board, but particularly negative in milk, grocery, and delicatessen, and detergents, paper. So these kind of represent our very low value customers. They're well below average in terms of values for each one of these 6 characteristics. And in fact, it's roughly analogous to cluster 4 from the k-means scheme, where we have negative values pretty much across the board, with particularly negative values for milk, grocery, detergents, paper, and somewhat delicatessen here. So it looks like clusters 4 for both the hierarchical clustering scheme and the k-means are matching up. Now that's completely a coincidence. You're not going to usually see, the 4th cluster from your hierarchical clustering scheme matching up with the 4th cluster from k-means. That's just a happy coincidence in this case. So cluster 2 for k-means, that was well below average for fresh and frozen. Do we see something like that from the hierarchical clustering scheme? No. Well, actually, yes we do. Cluster number 1, well below average for fresh, well below average for frozen, a little bit below average for delicatessen. We're seeing that these 2 clusters are roughly equivalent to one another as well. All right, well, cluster 2 here from the hierarchical clustering scheme, these are more or less our superstars, above average across the board, and that is roughly analogous to cluster 1 in k-means. They had a little bit below average in frozen, but above average for everything else. So we are seeing kind of a rough correspondence between the 2 clustering schemes. They're kind of agreeing as to what customers tend to be similar to each other. And that's some pretty useful insight. Remember that no clustering scheme is right versus wrong, only some that are more useful versus less useful. Here we're just getting 2 different perspectives. All right, question 4 asks us to take our hierarchical clustering scheme and add 1 more cluster. And you'll see what I mean by, business analytics really should be doing hierarchical clustering because it's so easy to do this. All right, so what I'm going to do is I'm going to add in 1 more column called HC5 to be the results of adding the cluster identities when there's 5 clusters involved. So with 4 clusters, we must have been cutting right about here. 1, 2, 3, 4. As we make 1 additional cut, it looks like this is the cluster that's getting split into two, and we'll be able to see that very clearly. So if I add in this new column and I now break everything down by HC5 here, here are my clusters that emerge. All right, so I'm going to run this aggregate command one more time. Put some space here. Here's 4 clusters. Here's 5 clusters. All right, so what we actually see is that we can match up clusters from the 4 cluster scheme to clusters from the 5 cluster scheme. You'll notice that cluster 5 here is the exact same thing as cluster 4. And in fact, if you look at the value for the original hierarchical clustering scheme with 4 clusters, you see this is basically cluster 4. This was cluster 3, this was cluster 2. It looks like cluster 1 got split up into this guy and to this guy. So we immediately know what to look at when we need to decide, okay, did adding in this extra cluster basically buy us anything new? So because we had that column that gave the column identity when we had 4 clusters, and now we're breaking every column down by the column ID when we have 5 clusters, we actually get a glimpse over, okay, individuals in this new cluster scheme with 5 clusters correspond to which cluster number in that previous cluster scheme. Since we see a duplicate of 1, we know that this is the cluster that got split into 2. All right, so did we gain anything by doing this? Well, let's look to see how does cluster 1 and cluster 4 differ, and is that difference meaningful? Well, about the same value for fresh, well below average, about the same value for milk, above average, grocery, both above average, frozen, below average here, detergents, paper, above average, delicatessen, cluster 1 a little bit above average, cluster 4 well below average. So was it worth it to go from 4 to 5 clusters? Well, the answer basically is it important to us to further split up those customers based on exactly what they're doing in terms of delicatessen spending? If this difference is interesting, finding one cluster that's a little bit above average and the other one that's well below average, then yes, going to 4 to 5 clusters is really quite important. If instead you talk to your boss and they're like, I don't really care what's going on with delicatessen, well then this extra distinction isn't really necessary. I don't need to go to 5 clusters because from 4 to 5 I'm only basically gaining additional insight in terms of what customers are doing in terms of this column. All right, so you can once again look at those official solutions if you want the text right up here, but that's basically the walkthrough. All right, this last question deals with something that's really interesting with customer analytics, RFM analysis, basically recency, frequency, and monetary framework. So very often what we do is we split up customers into a whole bunch of different clusters based on how recent customers have made a purchase at the company, how often they make purchases at the company, and how much they're spending. And so this data file contains a bunch of customer data, basically measuring values for each 3 of these different variables. And actually all the code's provided for you. So basically making a copy into data processed, taking out the ID column, which we don't need in this case because we're not going to be clustering on the identifier variable, and then going through and taking logs of everything. Now this last one, we're taking the log of the recency value plus 1 because some of the values are 0. We can't take logs of 0, so we add 1 to it. All right, we scale everything. We look at a summary, everything mean of 0. We could confirm that it's a standard deviation of 1. And what we're going to do is we're going to use the Ward D2 criteria for doing our hierarchical clustering scheme. We actually did that up here. So I'm going to borrow that code. All right, so it's up here is where I want it. My data frame is still called data.processed here, so let's take a gander. Here's going to be our dendrogram. Oh, this happens. So if this happens to you, no worries. Just start a new session. That autosave feature is great. Sometimes messing with the sizes of plots as R is trying to make those plots is going to make R crash. No big deal. We just go back to the file we were working on. We might have to read in some of those original functions. Might have to change our working directory back to where we want to be. But let's go down here. See, everything is still saved. Love the autosave feature. All right, so let's run through that code again. Let's make the clustering scheme. Let's plot it. Now with 4,000 individuals, this dendrogram is going to be a mess, especially at the bottom when a whole bunch of merging is going on all at once. But really what we're going to do is we're going to look near towards the top. So it tells us, all right, if we wanted 2 clusters, here are the individuals in cluster 1, here's the individuals in cluster 2. 3 clusters, we'd cut right here. Here are the individuals in cluster 1 stay the same. It's this right cluster gets split into 2. We wanted 4 clusters, well this far right cluster further gets split into 2, etc. All right, so what we're going to do is we're going to take 6 segments. Normally RFM analysis likes to find 11 clusters, and there's names for each of these clusters here, but let's let the data speak for itself. So we're going to take 6 segments, and what we're going to do is we're going to define a new data frame, processed with ID, to be a copy of data processed. And we're going to do data with ID to be a copy of cust here, because we're going to characterize these customers both on the scaled data and the original values of the data. And what we're going to do is we're going to add a column to them called ID that has the IDs of the clusters. So how do we get that out? Well, that's the cut tree command. Cut tree. Name of our hierarchical clustering scheme is HC, and we want 6. So same line of code for both here. We'll add in those cluster identities, and then we're going to use the aggregate function to find the average value for each variable for each cluster on the transform data, and then use the median on the original scale. So medians on the original scale, because things are skewed, the average isn't a good measure of the typical value. So we want the medians for the original recorded values, but the means for the transformed or processed values. So we're going to aggregate dot twiddle ID for data equals processed ID. And what function do we want? We want the average. And we're going to round this to just 1 digit. And we're going to do something very similar for the original scale, just there. So if we have 6 clusters, boom. Here's how we can characterize these 6 clusters. So what do we look for? Well, right off the bat, we look for the big positive and big negative values. So here we go. Cluster number 2 looks like, in this case, they have a very above average value for frequency. So these are very, very frequent buyers. They've bought a lot, but we notice they haven't, and they bought actually fairly recent. The recency is a little bit weird. 0 means they just purchased. 7 means their last purchase was 7 days ago. 100 means 100 days ago. So if we actually get a negative value here, that means they're well below average in terms of recency. That means they very recently purchased here. So what we see for cluster 2, these are our superstars. They've spent more than average money. They're visiting the shop more often than the typical shopper, and they visited more recently as well. So cluster 2 are our superstars. We like them. What's some other stuff that we can see? Well, we can characterize each one kind of one by one here. Cluster 4, I'll just go through one more. You can look at the full solution so you get a full breakdown of all these clusters. It looks like well below average in terms of the amount of money they've spent, below average in terms of the frequency of purchases, and well above average for recency. So it looks like these might have been maybe big one-time or maybe small one-time purchase customers. Let's actually look to see what we get on the original values. Those gives a little bit of insight here. So cluster 4 here, on average, or the median value for the amount of money, about $130. You notice that of these 6 clusters, that's the smallest value. Frequency, median value of 1. They've shopped there exactly 1 time typically. And when did they shop? Well, about half a year ago. So these are your one-time customers that made a fairly small purchase a while ago. If you want to increase engagement with them, well, that's up to the boss to decide. Cluster 2, those were our superstars. Notice the biggest median value for amount of money spent, biggest in terms of frequency, and also the most recent, only about a week ago here. So we could go through and talk about each one of these clusters. It's pretty interesting stuff here. We can treat the customers in these different segments differently. All right, the last part says, well, what if we were to throw in an additional cluster? What if we went from 6 to 7 clusters? What do we gain out of that? Do we gain additional insight? Would we say that this 7 cluster scheme would be more useful? So what we're going to do is basically just borrow this code from up here, and we're just going to add in one new column. So what I'm going to do is add in an ID 7 column, just to denote that, hey, there's 7 clusters here, to be the result of running ctree with 7 clusters. And then I'm going to aggregate using HC or ID 7 now. So break this down by the new column identities. All right. So one thing that I note, if I match up the new cluster identities with the old cluster identities, is that once again, I see a duplicate 1 in the ID column. That means cluster number 1 in my original scheme with 6 clusters got split into 2. Every other cluster is the same here. So I can confirm that by going back. I see that cluster 2, 0.7, 1.6 minus 0.3, 0.7, 1.6 minus 1.3. Every cluster except for cluster 1 is going to be the same. Cluster 1 got split into 2. So all I really need to do to decide if this new scheme is worth it is to look to see, all right, well, what are the 2 new clusters that emerged? This came from cluster 1, and this came from cluster 1 as well. So what am I seeing? Well, they both have typical values of 1 for frequency, so these are both one-time buyers. Recency is still, pretty big here. They haven't purchased in a really long time. Really how these 2 clusters are different are in terms of their typical values of monetary. So it looks like the new cluster 1 are the ones that made a really big but one-time purchase a long time ago. Cluster 4, well, they made a one-time purchase that really wasn't quite as big. So is that an interesting distinction? My hunch is no, but who knows, maybe the boss actually finds that really interesting. But that's why I like hierarchical clustering so much, especially in business analytics. It gives you a really easy way to talk about, all right, if we add in one additional cluster, how does that change our impression of what the individuals look like? We only have to focus in on that one cluster that got split into 2 to do a good job of talking about what that additional cluster bought us. And that's it. We're done.